So let's finish the IR lecture. It shouldn't take the whole time. The last few minutes I can answer any questions you have, and I want to go over a couple of things with you that I noticed while grading your lab reports in terms of answering questions. Because remember guys, the exams and quizzes not only covers what we cover in lecture, it's heavily based on lab as well, because lab is the applied for what we talk about in lecture. So it's as important as lecture material. The other thing I want to remind everybody, actually I can do that now before starting. I want to show you on Moodle that I put up answer key to the questions of the lab report. I also put an example lab report. So far I put GC example. I haven't put an HPLC example. I might use one from last year. But I also put the key for exam one from last year. So it's very important when you're done studying to try to solve exam one. Like I said, it won't be the same, but there will be related information. And it will give you an idea of what the exam will be like. So basically, I want you to succeed. That's why I provide you with these lots of things to look at. So you have used these tools. First of all, you have the key of this year's quizzes. So far we've got quiz 1 and quiz 2. Here, if you look at sample quizzes and exams, I've posted exam 1 and the key. Okay? Try to solve exam 1 before you look at the key, and then look at the key to see the level of detail that you needed. And don't solve before you study. Quite a study first will be good. And then here are other resources. So if you go to lab report questions, so far we have the first 4, nutrition labeling, accuracy, GC, and HPLC key. It's very important that you look at those. Sometimes questions in the exam come from questions in your lab reports. I will post the AA and MS on Friday as soon as everybody turn in their lab reports. So I'll post those as well. So these are helpful to look at after you study so that you test your knowledge. Okay? All right, let's finish up IR. Okay. What are some applications of IR spectroscopy? Katie. Okay, so we can do quantification such as using mid-IR or near-IR instrumentation for compositional information for online processing. These are secondary methods. Oh, I answered this one. They're secondary method because you use primary methods or official methods. Okay. Use official methods to calibrate the instrument. Okay. Structural elucidation and identification. So these are some applications of IR. What is the difference between dispersive and Fourier transform IR? So when we say dispersive, what are we dispersing? Molly?
The light.
We are dispersing the light, and we're using a monochromator. So only one select wavelength is being projected to the sample and absorb at one wavelength, which is no longer applicable. In Fourier transform, all the light is projected to the sample, and absorption at multiple wavelengths occur in the IR region. And then calculations, Fourier transform type of mathematical calculations, are done to get quantitative and qualitative data instantaneously at multiple wavelengths. So what is the type of energy that is absorbed, Ted? Vibrational energy. So in this region of the spectra, IR, this is vibrational energy due to the bonds that are in constant movement. Once they absorb, there is a change in the amount of vibration that is happening once they absorb light. And we already answered the fourth one. Okay, so we were talking about mid-IR, but we didn't get to Raman spectroscopy. Raman spectroscopy is a branch of mid-IR spectroscopy, and it's a very unique spectroscopy that helps with structural elucidation, and it's very sensitive, and water does not, there's no obstruction from water absorption of IR radiation in this spectroscopy. So it's very important because the band of water will not cover other bands. Okay, so what happens in Raman spectroscopy, there is scattering of light. First you have the Rayleigh scattering of light, and you have Raman scattering. So what does that mean? So when the photon hits a molecule, the photon gets scattered, and that's Rayleigh scattering. The energy of the scattered photon is the same as the energy that hit that molecule. Whereas Raman scattering, so here the photon hits the molecule, part of this energy gets absorbed, and the remaining energy is scattered. So that means that the scattered photon carries information about the molecule that scattered that light. So the scattered photon will have less energy because part of the energy got absorbed. Okay? That's Raman scattering. The scattered of a photon with less energy. So Raman spectroscopy can be used to observe symmetrical vibration. You don't care much about this information, that's just knowledge. Source of radiation is a laser, and you can do quantitation because the amount of light scattered, or the light scattered, is proportional to the concentration of the scattering molecule. So you can do quantification. It's applicable to solid and liquid, as I said, because water is not a problem in this spectroscopy. It won't absorb or won't scatter light in that way. And the spectrum that you obtain is less complex and more specific. So moving to near IR, this is another form of IR spectroscopy, mostly used to measure composition of solid foods. It uses diffuse reflectance. That, if you remember diffuse reflectance, so the light will penetrate short distance, some molecules will absorb, and the rest of the light will be reflected. So here's how it is. You have the light, the light that hits your sample. Some of it reflect without any absorption. Others will go in a little bit. Some of the molecules will absorb, and the remaining light will get reflected and be detected. And that carries the compositional information. That carries the information of the chemical constituents that absorb the radiation, and from there you can do mathematical calculations to calculate the concentration based on the reflected light. But importantly is when you prepare your sample or when you put your sample in the cell, it has to be homogeneous. Particle size need to be homogeneous, otherwise you will have different type of reflectance and scattering of light if you have larger particles and smaller particles. So it's very important to have controlled particle size and shape. That means with grinding, you would have homogeneous particle size. So those of you today that were grinding the almonds, we didn't have completely homogeneous sample, but we said, okay, we'll take the region that was ground, and those larger pieces, we won't use them. But in this case, we need to make sure that everything was ground to the same particle size. So unlike mid-IR, you would see the peaks are not sharp and nice like in the mid-IR. They're mostly white peaks, so we call them overtones and combinations. Sometimes the peak is actually composite of multiple constituents. They do something we call deconvolution of the peak. So it's a mathematical calculations where we divide the peak into multiple components using math. And mostly the IR and near IR absorption is of functional groups that have a hydrogen atom attached to either carbon, nitrogen, or oxygen. So i.e. common groups in water, proteins, lipid, and carbohydrate. So here are the functional groups in the main components of compositional or constituents. So you can see for water it's about the OH, but there are different band length or wavelength at which the OH will absorb. So the one at 1920, for example, it's combination of stretching and deformation, where the other one is only stretching. So, and then you have the protein, they absorb at 2 different ranges, and the lipids as well, and the carbohydrate. So you can see there might be overlap. So here, for example, you might have overlap between the protein, say, and the carbohydrate in this region. There is some overlap. That's why we look at both regions if we want to differentiate, and the math takes into account both regions. So here's how the spectra looks. It's not as pretty as mid-IR. And for example, cheese is high in moisture, so you see the moisture region really large and kind of over covering the protein region. So for example, egg and wheat have less moisture content, so you can see the protein more better. So, but that doesn't mean you can't measure proteins. You just have to do certain, or the program will do mathematical deconvolution of the peak to calculate the moisture from the protein from the carbohydrate. So radiation source is tungsten halogen lamp. You can use quartz as an envelope. It does not absorb IR in this region. The instrument can either be a monochromator or interferometer. Remember, we talked about having interference of waves, so you can either increase the amplitude or decrease the amplitude based on what you want to measure. And if you have an interferometer, you will have rapid scanning, and you would have measurements quicker, and then you use Fourier transform technology to make the calculations. And then these are the detectors. You don't need to remember that. Measurement is either reflection or transmission. If it's a solid, it would be reflection. If it is a liquid sample, it would be transmission of light. Like I said, you can do qualitative analysis by identification and looking at structure or molecular groups, or you can do quantitative analysis as a series of regression mathematical calculations to come up with the concentration of each constituent based on where they absorb light, and sometimes they absorb at multiple regions, and that goes into the calculation. Calibration is key. We have to calibrate using samples of different percentage of constituents to make sure we have calibration curves and the equipment is giving us as much of an accurate result as possible. And then we do validation by getting a set of samples and run it through that. We know the concentration within these samples, but we run it through anyway to test the calibration. So it is used a lot for cereal products, grains, oilseed, just to get composition and analysis, and it's used for dairy products. Remember, calibration is key for quantitative analysis, and it's often used to identify contaminants. Here's an example where melamine was run and an infant formula was run to determine if you see some of the banding absorption of melamine, to see if the infant formula has been contaminated with melamine. NIR can be used for online measuring of constituents during processing. Well, yes, I was just talking about that. Okay, here's a good summary of advantages and disadvantages for you to look at that would compare mid-IR to near-IR. Well, that's it for the IR lecture. Questions in general about the exam? Yeah. What's that? He's done with the moisture. I think he needs to finish that, and then on Wednesday and Friday he'll go over water activity. So he's coming back Wednesday and Friday. Originally we had the exam, so I didn't put this on his schedule. So that's why I'm here. But there is no moisture in the exam for the exam. Anything you want to ask about content-wise? You haven't studied yet. Okay. Huh? Molecular. Walter. There is no multiple choice and there's no true and false. So it's all questions that are written. It would be great if you come 5-10 minutes early so you can start with the exam so you don't feel rushed. Carmen?
Are we going to need to know specific calculations? Like, we already know the precision calculations and stuff, but like Beer's law and all of those other
Beer's law, you need to know Beer's law. You need to know absorption equal A, B, and C. You need to know what A is, B is, and C is. Yes, you need to know this. But there's not calculation. I can tell you, I don't know if there is calculation about standard deviation or coefficient of variation. You might want to get your calculator to be on the safe side. But this is not a heavy exam on calculations. I saw a hand up here. No? Did you have a question? No? Okay. So I want to remind everybody that Chelsea on Thursday would be in the lab.
Up in 223 ABLMS, there's whiteboards up there from
Okay.
3 to 4.
Okay, 223 ABLMS from 3 to 4 is her TA hour. And if you want to have a study group, you can come and ask each other and answer questions, and Chelsea will guide you. But as I was grading GC lab reports, I noticed most of you, or many of you, answered the internal and external standard question incorrectly. I want you to understand the difference and understand why we would use either or both. So let me ask you this. Why do we use internal standard if we have internal standards? Why is it important? Can anybody? Yes?
To account for any loss in sample preparation, especially if it's a long sample
That is one important reason. If you have a lengthy sample preparation, adding an internal standard to all of your samples is very important, because any losses from your sample, your internal standard will get the same losses. Also, the injection volume, any error because of injection volume will be the same for your internal standard and your samples. But can you quantitate with an internal standard alone? Why no?
Well, you'll need an external standard to run to compare the losses to. If you don't have anything to compare the amount of sample loss, you don't know how much you lost.
Okay, we need an external standard, that's true, but if you don't run an external standard, you don't have a calibration curve or standard curve. Remember, your standard curve, you run known concentrations at different concentrations, 4 or 5, and you plot your standard curve. If you don't have a standard curve, you cannot quantitate. How are you going to relate concentration to response factor, whether it's an absorption or a flame ionization detector response? You need the response at different concentration. You cannot, most of you said internal standards are important for quantification. Without an external standard, you can't quantitate, period. So if you don't have an external standard, you can't quantitate. If you don't have an internal standard, you won't be able to correct for sample preparation errors and injection volume. Having both would be great. And would you need to add, if you have an internal standard, do you add it to the external and the sample, external standard and the sample, or just the sample? Both. Because when you plot your standard curve, it's a ratio of the area of your standard, external standard, by the ratio of your internal standard. So it's a ratio. And your area of your unknown is also a ratio of your unknown concentration or area to the area of your internal standard. So you have the ratio. So you need it to be in both standard, external standard, and sample. Okay, so make sure you review the key for that particular question. And I saw also some of you confused about what we mean by response factor. Even when I was looking at some of your lab notebooks today, one of you said, or some of you said, explain to us more response factor. Okay, so what is a response factor? What does that mean? Anybody? What is a response? So in HPLC we had an absorption, UV absorption. So the response was UV absorption, right? In FID, what is the response? So your sample get ionized and then they get detected by, so they get ionized by a flame and then they get detected. So what's detection of ions? Is there a specific name for that? Current, change in current, thank you. So the change in current based on the presence of ions. So that's your response factor in FID. So response factor in MS, there is no response factor. It's abundancy of the ion. How much percent abundancy is your ion? Okay, so that's what is meant by response factor. Now, each compound will have a different response factor. Take absorption, for example. Each compound has unique absorptivity. So so let's say we talked about diazine, so this would be relatable. Diazine, and then you have genistin. One has lambda max of 249. One has 259 lambda max. So if I'm just measuring at 259, not at 249, I just programmed my UV detector to just measure at 259. So 1 milligram per ml of diazine might give me this area. So that's absorption. here, and this is time. And then 1 milligram of genistein might give me this area. Same concentration, but different responses. That's what we mean with the response factor. And that's why your GC method was semi-quantitative, because we didn't get the response factor for each FAME and did the external standard curve. We didn't do that. So that's why we just did relative areas. So we didn't have the unique response at different concentrations of each FAME, whether it's linoleic, how do you say it, linoleic, yeah, or oleate, all of these different ones, they will have different responses. That's why for quantification, you need different standards. So I also saw that some of the answers was we didn't weigh the sample, we just put a drop. Well, it doesn't matter if you weigh or you don't weigh. When you're doing semi-quantitative, you are looking at relative percent area within that one drop. So you're not comparing sample A to sample B. So within that one sample, you're looking at the relative area. So when you're not quantitating, it doesn't matter. So that one drop doesn't matter. Okay, so these were based on what I've seen from grading lab reports. Any other clarification you would like to go over? Okay, if not, guess what? I'm going to let you go.